Um, Hello all. My name is Bobby Reiner. I'm an associate professor in the Department of Health Metric Sciences. Before I get to introducing Joey, I just wanted to talk a little about the format for this defense. Joey is going to, I'm going to introduce Joey, then Joey is going to present the results of his dissertation, at which point we will then open up questions to the general public. Anybody can ask any question. Throughout the dissertation, if you have a burning question, please put it in the chat, and then we might pause to get to it, or it might build, and that might be one of the first questions during the Q&A session afterwards. Once the general public has asked their questions, Joey and the committee will sequester ourselves to a different virtual room. Everyone else is welcome to stay here, where we will then grill him. We'll ask him more questions about the work, and then upon him answering those questions, he will then leave that room. He can come back here. He can do whatever he feels like doing. We will have a brief or long discussion depending, and then we will come back here to deliver our final conclusions and decision. Excellent. There's multiple people that are going to be keeping an eye out if someone starts talking, so please do not be offended if you get instantly muted. That being said, so I joined IHME about 7 years ago, and by that time, Joey was already well established as a member of IHME. I didn't know him personally until I served on the PhD admissions committee in 2017, where I was actually one of the people who interviewed him. I was extremely struck by his passion, not only about the environment and health, but about the environment and health and the Pacific Northwest. I then, unfortunately, maybe for him, was assigned his advisor, where he worked on not environment and health in the Pacific Northwest. Instead, he did some pretty amazing work for the local burden of disease team, looking at, well, he'll talk about that as one of his aims. But fortunately, once he was able to get through kind of that gauntlet of doing work that somebody else was more interested in than him, he was able to focus again on environment, health in the Pacific Northwest. And it's been an absolute pleasure to work with him. He's extremely bright. He's extremely enthusiastic about the work. I think we almost never actually get to the end of our agenda, even though we have hour-long meetings on a regular basis. Just talking about the math and the impact, but it's been an absolute pleasure, and I am excited to hear about these results. And with that, I will turn it over to Joey.
Thanks for the introduction, Bobby, and thanks to everyone for coming. Happy Friday. I'd like to present to you the results of my PhD dissertation work. They're titled Global Metrics, Local Estimation, Magnifying the Impact of Environmental Justice. So just to briefly give you an outline of this talk, I'm going to first discuss a little bit of the motivation for this work. Then I'll go over some results from the first chapter, which is about geospatial mapping of household air pollution. Then we'll look at the second chapter, which is a global sensitivity analysis of the Washington State Environmental Health Disparities Map project. And then in the third chapter, we'll do some case studies of that EHD project in order to answer some of the questions that arose during the second chapter. And finally, I will give my conclusions, and then we can pause for a Q&A. So to talk a little bit about the motivation for this work, in the 1850s, the godfather of epidemiology, John Snow, discovered for the first time the association between the health of an environment and its inhabitants when he was studying the link between the Broad Street pump and cholera mortality in London. In the years since, many researchers that have followed him have discovered different factors that impact human health and a variety of different pathways through which these factors impact it, whether direct or indirect. And we know that disparities in these factors will manifest in inequalities in health outcomes. In order to make informed decisions, it requires us to make robust, high-resolution estimates of these disparities. But anytime we're mathematically modeling complex systems, it's going to require us to make assumptions, and it will introduce bias. As such, in order to make effective policies, we need to understand both the extent of these problems and also the limitations of our solutions. So some context for the first chapter. Currently, billions of people do not have access to clean energy, and as such, they primarily do their cooking using solid fuel sources. Solid fuel sources generate fine particulate matter, which we can call household air pollution. And that fine particulate matter in households was associated with more than 2 million deaths in 2019. The Sustainable Development Goal number 7 has a target of universal access to clean cooking and energy sources by 2030. And a departure in the SDGs from the preceding millennial development goals is a focus on inequality, as it was realized that many of these goals were not going to be met, not because countries were not making progress, but because that progress was not uniform across countries. We know that there's a lot of local variation in environmental risks and specifically solid fuel use, and that drives inequalities, but these had yet to be quantified at a subnational level. So this is some work that was published in the Lancet Global Health in 2022, and I'm going to go through some of the findings that I thought were most interesting and exciting. So in order to answer this question, first we needed to look at the available data, which is typically from household survey conductors that go to a house. They'll ask a battery of different questions to the head of the household. And one of these questions that's relevant to our work is, what is the type of fuel that your household mainly uses for cooking? You can see in this particular survey, which is from the DHS, there's a variety of different responses here. And we mapped those responses to the most common ones, where the first 3 are no cooking, cooking using electricity, or cooking using gas. And those were mapped to a binary variable of clean fuel use, which is aligned with that SDG target of universal access to clean fuels by 2030. And the bottom 4, which are the ones that generate the most fine particulate matter, coal, wood, crop, and dung, were mapped to solid fuel use, which is aligned with another SDG target, the mortality that's attributable to household and ambient air pollution. And we'll talk about the interaction between those 2 factors a little bit later. So we looked at all the data that was available across 98 different countries, which were all the low and middle income countries that had this type of household survey data available for our use. Incorporated about 2.1 million households. And here's an example of what that data looks like in Africa. You can see what it looks like over time. And we can also see that while the coverage of the data is decent, there's definitely some gaps in time and space. And so that meant that we can use some modeling approaches to try and fill in those gaps. So how do we do that? We collected 25 different geospatial covariates that had potential relationships with household air pollution and solid fuel use. These covariates came from a variety of different places. Some of them are environmental, such as the elevation. Some of them have to do with population, such as the population density. Some have to do with development, such as fertility rates. And we combined these covariates and that household survey data in a geospatial model, where we used 3 different submodels to analyze the relationships of those covariates with the data, and then also use some spatial effects in order to incorporate the spatial structure of this data, which is an important thing to think about because, as with many factors, environmental factors in particular tend to have a lot of spatial autocorrelation, and this is something that needs to be accounted for in the model and can also be used in the model in order to make estimates with higher precision. I think it should be obvious to everyone that places that are closer to each other in space and time are going to tend to be more similar, and we can use that effect in order to improve the quality of our predictions. So we made estimates of the prevalence of solid fuel use or household air pollution, which can be thought of as the probability that in a given place, a household is using solid fuels. So you can see this color scale is rising from very low probabilities to almost universal use of solid fuels. And we can see that these areas of really high solid fuel use tend to be concentrated here in sub-Saharan Africa, but that there are also places here, such as India, where we can see really some stark divides between parts of the countries. And I think this highlights the benefit of geospatial approaches and making subnational estimates of these risks. So we can also combine this data with some other data sets that are available to do some post-processing and answer some other questions that are related to this. So one of the things that we did was take these estimates of the probability of solid fuel use, and then combine them with estimates of the expected PM 2.5 emissions in a household that is using solid fuels to get an estimate of that household air pollution exposure. We also combined that with estimates of ambient air pollution or the outdoor air pollution in that area in order to calculate total air pollution, which we're calling TAP here. And by way of the two constituents going into total air pollution, the ratio of ambient air pollution to household air pollution. So that's kind of telling us which of these two sources is driving the total air pollution. So we can look at that metric over space and time, so this is for 2018, which was the latest year of our study. And here we have this bivariate color scale where as things become more gold, that means that the share of this air pollution that's being driven by household sources is larger. And as it becomes more purple, that means that the density or concentration of total air pollution dose that a household in this area is receiving increases. So I think it's interesting to look at this dark brown area, which are places where they're receiving very high doses of air pollution that's almost entirely being driven by household sources. We can also look at this like more purple area, which we can see kind of parts of northern India and also eastern China, where there are similarly high doses of air pollution, but they're being mostly driven by ambient sources. Another thing that we can do is look at these estimates, which were made from 2000 to 2018, and look at the patterns and time trends therein, and then make forecasts to 2030, which is the goal for these SDGs, to see whether or not these countries and subnational units are on track to meet this SDG goal. So if we look at the rate of change in solid fuel use from 2000 to 2018, you can see a pretty stark finding again, where in sub-Saharan Africa, there's been very little change in solid fuel use. As it becomes more purple, that means solid fuels have decreased more of that time period. And again, we can look at India and see that there's been relatively little improvement in this northern area, but quite a lot of improvement in southern India. So I think it's no surprise that these translate to whether or not, based on this current trajectory, a given unit is on track to meet the SDGs. And we can see here this dark red area is with very high certainty they're not on track, and the light blue areas with 95% certainty they are on track. And so again, I think we've reinforced this point that sub-Saharan Africa has made very little progress on this risk and is not currently on track to meet this goal. And I think we can look again here at India, where we can see a pretty stark example of places where they are on track quite near to places where they aren't. So I think this really highlights the importance of these subnational estimates and how at a country level, it might obscure the true patterns on the ground of whether or not places are on track to meet this goal. The last thing that we can do is use information about the relationship between total air pollution and health in order to calculate the burden on health from total air pollution. So we ran these estimates of total air pollution through a dose response function, which tells us the increased risk that a individual who is facing this level of total air pollution is going to face, and that will give us a population attributable fraction, which is essentially the percent of that disease burden or that health outcome that is associated with this level of air pollution. And then we combined that with estimates at the same geospatial resolution of the mortality or deaths from lower respiratory infections, LRI, for children who are under 5. And we did that because lower respiratory infections are one of the key drivers of under 5 mortality, and child mortality is a broad goal of the SDGs as well. So we can combine those to tell us the amount across time and space of lower respiratory infections for children that are under 5 that are being driven currently by this total air pollution burden. So this is a density plot. And a density plot helps show distribution of populations according to a variable, where as the density rises, that means that there's a greater concentration of populations in that area. And the x-axis here is the total air pollution as measured by micrograms per cubic meter of PM2.5. And we can see here that the x-axis is being plotted on a log scale. And I think that's an important thing to reflect on for PM2.5, because research has demonstrated to us that PM2.5 has a dose response curve that's super linear. What that means is that risk rises very sharply in the first amount of exposure and then tends to plateau with later levels of exposure. So really like the most important parts of PM 2.5 exposure are down in this part of the plot. And then as it rises further and further, the subsequent additional health risk is less than it was in this beginning part. So on the top of this, let's focus first on the top part, which is about population. And above the x-axis is the distribution of population in 2018. Below the x-axis is the distribution in 2000. So let's just focus on one country, China, which you can see here in kind of this tomato red color. And the shaded part of this distribution is the contribution to that total air pollution that's coming from household sources. And the lighter part is that which is coming from ambient. So we can see that over this 20-year period, China's air pollution or the levels of air pollution that China is facing has been nearly halved, or maybe a little bit less than half, as populations have moved closer towards safer levels of air pollution. But this blue dotted line here represents the WHO's interim target or annual exposure to air pollution of 35 micrograms per cubic meter, which I think it's important to note that this is not understood to be a safe dose. Safe dose is like really more something like 3 to 5 micrograms per cubic meter. So this is really just kind of like an interim target to work towards on the way towards making these doses or making sure that these populations are exposed at lower doses. So really what we can see is that in 2000, none of the population in China was at this target, but now we can see based on the shift that a small part of this population is below the target, but they're still being exposed to levels of air pollution which are substantially above that of even the interim threshold. Now on the bottom, we have the same thing except for deaths from LRIs. And I think let's look at India as an example here, which is this purple country. We can see here that compared to population, deaths from lower respiratory infections tend to occur at much higher levels of PM 2.5. And in the year 2000, most of the deaths from LRI in under 5 in India was being driven almost entirely by household air pollution. Now those deaths are happening at lower levels of air pollution, and ambient air pollution has taken up a lot of that impact as household air pollution has fallen, but we can still see that all these deaths are happening at a much greater level than this interim target, and that they are still happening at substantial levels. Here, we're looking at something like 300,000 deaths in 2018 from this risk factor, whereas like something like 600 or something like 800,000 in 2000. But obviously, I think we can both agree that while this has been a substantial improvement, 200,000 deaths from a preventable risk factor is not acceptable. So what are the key points that we can take from this work? I think it demonstrates that space matters. The place where you're born can really strongly predict what the quality of your life is going to be and even how long that life is going to be. And I think space matters at a fine level. And we can see that these geospatial estimates show us that there's substantial inequalities happening at a subnational level. And if we want to hit this SDG target, we need to dramatically accelerate the transitions towards clean fuel. And these this lack of transition or our slowness on tackling this risk factor has huge impacts, and there's a lot of preventable deaths that are occurring and will continue to occur until we accelerate this. Now, how does this motivate us for chapter 2? It also matters here. And environmental inequalities have persisted and even grown in the United States and also within our own state. And I think the events of the past few years have really demonstrated the unequal burdens that are faced by people in our communities. And I think that we only need to look at the air pollution that's going on in the Northeast and New York City to see that climate change is going to increase the effects of inequalities in environmental risks in both our lives and on the lives of our neighbors. So that brings us to chapter 2. There's a broad movement for environmental justice worldwide and in the United States, and there's a number of different data-driven tools that are being used federally and at the state level, and they're often being used to allocate funding and resources for how to tackle these environmental problems. The Washington State Environmental Health Disparities Map, or the EHD, which we'll call it from here on, is an example of one of these tools. It's a government academic partnership that is led by community members. And the goal of it is to estimate impacts of cumulative or rankings of cumulative impact from environmental health disparities by synthesizing 19 different environmental and population indicators. Now, we know that composite indicators, whenever you construct them, can be sensitive to the methodological assumptions that were used to build them. However, these environmental justice indicators have never undergone a comprehensive sensitivity analysis. So, and here we have a map on the right side of what this indicator looks like in Washington State. And you can see that it creates rankings that are in deciles going from 1 to 10, where 10 is the most environmentally impacted. And we can see that high impact tends to be clustered here in the South King County and Pierce County areas, parts of Vancouver and in Spokane, and here through the Yakima Valley region, moving towards Tri-Cities. Now, another important thing to consider is that under the HEAL Act, or the Healthy Environments and Living Act, there's federal funding that's available for these communities, and the EHD map is currently being used to decide how that funding is allocated. And the top 2 deciles, or the top 20%, or places that are ranked 9 or 10, are classified as highly impacted, and they're eligible to receive this funding for environmental remediations. So we can see kind of where those places are located. So this is important from a policy perspective, because whether or not you're in this category means whether or not you'll be getting funding. Now, one thing, so there's been 2 versions of this index that have been produced, and by comparing the version which came out last summer, version 2.0, to the first version of it, one thing that we observed is that census tracts moved in or out of this impact classification based on some minor methodological changes and data updates. And so we can see places in purple that were added to the top 20% and places in orange that dropped out. So this is a big motivator of the study in terms of trying to ask what it is that causes places to move in or out of this funding threshold. So how is this score created? First thing that needs to happen for creating a composite indicator is to select the indicators that are going to go into it. We can see that there's 19 different indicators here, and that they fall into 4 different groupings. Two of those groupings have to do with characteristics of the population that might make them more sensitive to environmental health impacts, sensitive populations, and socioeconomic factors. And then 2 of them have to do with ways of measuring the pollution burden or the environmental health impacts. Some of them are more direct, which are exposures to these environmental risk factors, and some of them are more measurements of environmental degradation that could then translate to more indirect impacts on health. So the next thing that needs to happen is the indicators need to be measured. So an example that we've been talking about, PM 2.5, in this version, it is being estimated by the Department of Ecology, who are using ground monitoring stations that are spread across the state, which measure the concentration of PM 2.5, and then they use a spatial model to smooth across that. The next step is that the indicators need to be normalized, and that's important because, you know, we have just been talking about how PM 2.5 is measured with micrograms per cubic meter, but something like cardiovascular disease, for example, is measured as a rate per 1,000 or per 100,000 population. So these indicators are going to be in different unit spaces, and in order to combine them effectively, we need to standardize them to the same unit space so that we're not comparing apples and oranges. The next step is to create a hierarchy. We can see that in this version, there's a 3-step hierarchy with these 4 different theme groupings, and then there's these super themes, of which there are 2, and then the 3rd step, which is to create the final score. Another potential step is to decide how you want to weight things. So the only weight that's being applied in this index is a 50% down weighting on the environmental effects category, under the with the understanding that these are less direct and more distal to health impacts when compared to environmental exposures. But I think one thing that's important to keep in mind is that through the hierarchical construction of this index, there's also some implicit assumptions about weighting. So there's only 2 variables that are in the sensitive populations category compared to 7 being in the socioeconomic factors. So as such, these are going to be inherently having a higher weight than those in the socioeconomic factors. Next step is to aggregate these. And so what's being done in this index is to take the arithmetic mean of each of them at every step of the hierarchy. And then at the last step, the pollution burden score is multiplied against the population characteristics score. So it's taking a product of these two things with the idea that there's some kind of multiplicative interaction between these that has an impact on environmental health. So how can we look at the sensitivity of this index? Obviously, there's a number of different decisions and assumptions that have been made in the current version, and these are not necessarily the only ways to calculate an index like this. So what we did was look across the literature of all different environmental and socioeconomic composite indicators and see what other types of methods could be used for each of the steps that I just discussed. Then we created a sample space of all the different possible combinations of methods that could be used. And then we quasi-randomly sampled from that space using a Sobel sequence, which is a way of more efficiently searching a sample space to try and hit as many different areas of it as possible. And we did this 110,000 times. And we can talk about what one hypothetical simulation would look like. For example, some measurement error simulated into it to see how sensitive these indicators are to errors by like adding some random bias, dropping one of the indicators at random, potentially using a different method to normalize them, potentially instead of using this arbitrary weighting scheme, use some kind of weighting scheme that's driven by the correlation structure of the metrics. Potentially, instead of using a hierarchy, just collapsing all the indicators simultaneously in one step. Maybe instead of using the arithmetic mean, it was using a geometric mean to do this aggregation. And then instead of classifying high impact using deciles, perhaps it was using equal intervals. For every one of these simulations, we calculated a statistic called the mean absolute rank change, which we'll call the mark from here on out. And basically what that's doing is comparing the rank that was generated across these census tracts for this simulated version to the baseline rank, and then taking the absolute value of that and then taking the mean of it across all the different census tracts. So essentially what this is telling us is, on average, how different is this simulation from the current method? Now we can look at that value across these 100,000 simulations as a way of asking, or of comparing the average way of calculating this index according to the literature with the way that we're currently calculating it based on the EHD paradigm. So what we're looking at here is the median of those simulations. So what the average construction of the index looks like, subtracted from the baseline. So in places where this value is blue, that means that the baseline was higher than the average way of simulating it. And where they're red, that means that the baseline was lower. So one way to think about this is that compared to the average way of constructing this index, where it's red, that means that the baseline is currently underestimating them. So we can see that the baseline tends to be higher in some of these places in North Seattle and moving up the I-5 corridor, where it tends to be lower in kind of like southeast rural King and Pierce counties, and then also stretching through this Yakima Valley area and south of Spokane, so areas that seem to be more rural. I think it's also interesting to look at the range of the uncertainty interval across these 110,000 simulations as a way of trying to see how stable a given census tract is. So as this color scale becomes more yellow, that means that the range of different rankings that a census tract could receive varies widely depending on how you simulate it. Whereas it becomes darker, that means that range is a bit tighter, and as such, that census tract is more robust to changes in the method and is going to tend to get the same ranking. So one thing that is important to think about with this axis here is that it goes up to like 1,000 or about 1,500, and there's something like 1,490, so about 1,500 census tracts across the state. So in a place here like Okanagan County, where the average uncertainty interval is around 1,200, really that place could fall almost anywhere in the spectrum depending on how you calculate it. I think it's even more interesting if we combine that metric of uncertainty with a metric, or with what the ranking was in the baseline EHD. So here we've created another bivariate color scale, where as it becomes more red, that means that the EHD is ranking it with higher environmental impacts. And as it becomes more blue, that means that the uncertainty interval as measured by these simulations is larger. So I think it's interesting to look at these places where it's kind of this tomato red color. These are places where it's currently being classified in the top 20%, so it's eligible for funding, and there's high certainty. So really, depending on, it doesn't matter how you calculate it, it ends up in that funding classification. Then if we look at this more purple area, we can see that these are some places where there is high impact currently. It's being classified in the top 20%, but the certainty is pretty low. So if you calculate this index in different defensible valid alternatives from the literature, it may not actually end up being eligible for funding. And the same thing on the other side. We can see places here where it's currently being classified in the bottom 20% of impact, but there's low certainty. So really, depending on how you calculate this index, it could potentially move in or out of this funding threshold. We can also look at the census tracts in order to compare their uncertainty as a function of their baseline EHD. So here on the x-axis is the ranking of a given census tract from 0, or the lowest ranked census tract in the baseline EHD, to 1500, which would be the most environmentally impacted according to the EHD. And the y-axis is greater uncertainty. And then each of these hexagons represents the clustering of census tracts within them. So as they become more dark, that means that there's more census tracts falling in that area of the plot. So I think it's interesting to observe this parabolic shape, where as we move closer to the middle of the environmental impact, the uncertainty rises. You can see it can be like something like 1,000 ranks up here, on average around like 600 to 700. So if we think about that in terms of the space of rankings, that means that it could be moving somewhere from the middle towards the top, or down closer to the bottom. So really, depending on where you fall in this, the method that you use to calculate this index could shift a given tract all over the place. Now, this dashed line here is the cutoff threshold for funding, so the top 80%. And I've overlaid on these census tracts a color scheme that was created by comparing the first two versions of the EHD. So if it's blue, that means that both versions agreed that these fall in the bottom 80% and are therefore not eligible for funding. If they're this tomato red color, that means that both versions put them in the top 20% and agreed that they're eligible for funding. And if they're yellow or if they're orange and yellow, that means there's some disagreement. So I think it's interesting to see. I think one thing that's important to note is that you're usually going to tend to see this kind of parabolic shape when you're estimating sensitivity or uncertainty across this range, because things that are on the extremes of the range are going to be bounded by the minimum or the maximum. So the amount that they can vary is reduced. But I think it's interesting to compare the right side of this, where we see a lot of clustering with high impact, high certainty, to the left side, where there's some clustering, but there's also many points that have a much greater uncertainty. So to me, what this says is that this index seems to be most robust, and therefore not be shifting based on what method you're using in places where the impact is classified as high. So what's driving this? In order to answer that question, we can look at some statistics called the Sobel sensitivity statistics, which are a way of decomposing this variance into the incipient pieces. And essentially what these represent is—
Yeah, bye. Bye. I'll see you soon.
Essentially what these things represent is the fractional reduction in variance when a given parameter is fixed. And we calculated two different versions of these, one which is the first order, or the variance that's coming just from one parameter in particular, and the total order, which is coming from that parameter and its interactions with any other parameters. So on the left side, we can see that first order statistic. On the right side, we can see the total order statistic. And we calculated this for two different versions, one of which is the probability that a given simulation matched the same impact classification, or the accuracy. And the other one is the mark, which we've been talking about. So we'll just focus on the mark for purposes of time. And these are sorted so that the ones that have greater sensitivity are at the top. And what really jumps out is that the two methods that seem to be most sensitive are the aggregation formula and the method that's used to normalize the data. Another way we can look at this is by looking at the individual parameter selections within those parameter groups and see which ones were more different. So this is the 100,000 simulations, their distribution being graphed as a box plot, where this is the interquartile range and this notch in the middle is the median. And as things move further to the right, that means that that simulations that selected this version or this method tended to be more different from the baseline index. And so I think some key things jumped out here is that the two most different ways of calculating this index are methods that are inductive. So it's using a PCA to aggregate it or using inverse correlation to weight it. And these are methods that instead of us imposing our own understanding of what the hierarchy should be on it, they're using the correlation structure of the data to drive that. So those tend to be very different from the baseline EHD. Any simulations where we dropped death from cardiovascular disease or low birth weight tended to be very different. These are the sensitive populations indicators. And I think this makes a lot of sense given that these indicators only have 2 in the group and are therefore weighted more than others. And we also observed that normalization methods that use linear scaling approaches versus these nonlinear scaling centiles or deciles, which is what was used in the baseline EHD, tend to be pretty different. So what are some of the key things that we found in this analysis? There seems to be some sensitivity around that 20% threshold, and especially a lot of sensitivity in the middle of the range of impact. So that tells me that this method is better suited for classifying high impact than it is for measuring impact continuously across this range. And it also says that potentially we need to reevaluate what the threshold for funding is, given that relatively arbitrary decisions in terms of how the index are calculated could shift, attract, back and forth over the 20% threshold. It seems this index is very sensitive to the normalization and aggregation methods. So I think that raises the question of statistically, which are the most valid methods to normalize this data? And I think it also demonstrates that doing it deductively, as we've currently done, versus an inductive aggregation scheme are pretty different. So that raises a question of how confident we are in the theory that underpins using this deductive version of aggregation and our current hierarchy. So in order to answer some of those questions, we did some deeper dives with a case study in chapter 3. So the first thing I would like to look at is the distribution of these 19 indicators when they're collected as raw data. And so you can see that these are colored by theme and that they have a variety of different statistical characteristics. I think it's interesting just to zoom in on the environmental exposure data because these have a variety of different distributions and statistical shapes. We can see that ozone concentration and PM2.5 are relatively normally distributed, where PM2.5 has much more kurtosis than ozone, or there's a much greater density of that population that's concentrated within this mode. So there's very high probability that a given person in this population is going to be located at this area, PM2.5. Now, if we look at diesel PM2.5 or toxic facilities from RSEI, we can see that there's a ton of positive skewness here. And there's like some big outliers. And so that has crammed a lot of the distribution down here towards the left. So what happens to these distributions if we use different methods of normalizing them? We can see that these like more linear transformations of using min-max scaling or z-scoring, which are here in the purple and the red, tend to preserve the raw shape of that distribution. Whereas when we use centile and decile ranking, where essentially what we're doing is we're ranking all the tracks and then binning those into equal groups, either 10 equal groups in deciles or 100 equal groups percentiles. We can see that essentially what we're doing is assuming that this data has a uniform distribution because it needs to be uniformly distributed into each of those different groupings. And we can see how different that distribution might actually be than the raw distribution by looking at these blue and yellow plots. So what impacts does that have on the rankings that are produced by the EHD and also on the allocation of funding? In order to answer that question, let's look at 2 different case studies of particular census tracts. So case 1 is located in Okanagan County. It's a relatively rural county that's near to the Grand Coulee Dam and also bordering the Colville Indian Reservation. Case number 2 is located in Greenwood, north of Seattle. And we can see that here in yellow. And this is a relatively urban tract. I think that actually both Nancy and Joe live here, so they can tell us a little bit more in the Q&A about what this place is like. But I've heard it's pretty difficult. I think that one of the hardest problems is that there's not a PCC there. And so sometimes people have to shop for their groceries at Fred Meyer. And obviously, I think this is something that's not being incorporated in the EHD, but I think in future versions, it could be something that would be important to think about. So why did we pick these two things? Not just so that we could talk about Nancy and Joe's neighborhood. It's because these are two census tracts where there's the biggest difference in their scores between whether they're calculated using the baseline EHD nonlinear scaling method or using a linear scaling method of z-scores. And that difference actually causes them to switch their funding classification between being eligible for EHD funding or not eligible for it. So we're looking on the top here, we're looking at case number 1, Okanagan County, where this purple triangle is its score in the baseline EHD using nonlinear scaling. So this is the version that's currently being used. The orange version is a version that's being created using z-scores or a linear scaling approach. And these have been scaled to the same unit space where this black line represents the state mean and this blue line represents the threshold for funding. So we can see that Okanagan County in the z-score space is considerably above that line, something like the 97th percentile, and a bit below it in EHD, something like the 65th percentile. And here in Greenwood, we can see that it's just below the line using z-scores and a little bit above, something like 85th percentile if you use baseline EHD. So what's happening in these individual indicators themselves? So if we look here at the environmental exposures and effects indicators, we can see that so here I've plotted also the same thing with these points. That's its indicators score if it's z-scored, and in purple if it's centiled. And I've also plotted a box plot showing where the distribution of the state's population is located at. And we can see here this notch is the median of that distribution. And as the medians get further left of the state mean, that tends to represent skewness in that variable. So we can see what's happening here for Okanagan is that they have a really strongly outlying PM 2.5 value that is then being compressed down by z-score scaling. And in many of these other indicators for environmental effects, they tend to be closer to the median or within this IQR or somewhat like similar to the rest of the state. Now, if we look here at what's happening in Greenwood, really, there's not any major outliers here. Diesel PM 2.5 is somewhat high and quite a bit above the IQR, and ozone is pretty low. And for all other indicators, the value tends to be a bit above the median or a little bit above the 75% or percentile in z-score space or in the raw data. But in each of these cases, it gets stretched a little bit further by this nonlinear scaling when we use centiles or deciles to rank them. We can see what that's doing is pulling these values, which are somewhat close to the state average, further towards the right, and in some cases bringing them above that threshold for funding. So if we look at the same thing for the sensitivity and socioeconomic, or these like more population level indicators, we can see a similar effect that's happening. So here in this Okanagan County, it has really high values for a number of these different indicators, a big outlier for low birth weight, way above the state average for not having a high school diploma, for the population that's people of color, living in poverty, transportation expense, and unemployment. And in every case, we're capturing that effect in z-score space, and then that's being compressed much closer to the threshold and the state average when we transform that to centiles. Now, if we look at the same thing in Greenwood, we can see that most of these are, again, well within the IQR or close to the state average. And when they get transformed to centile space, each of them is getting pulled up a little bit closer to that threshold for funding. So if we look across all the different variables for what's happening in the state, we can see, generally speaking, the effect of outliers is compressed using centiles, and things that are much closer to the mode or the center area of the distribution are stretched a little bit further in this nonlinear scaling. And as such, this area ends up being bumped over the line to be eligible for funding, where this one gets compressed to be much lower. And I think an important thing to think about is that potentially compressing some of these outliers might not be a bad thing, because as we talked about with the shape of the risk curve for PM 2.5, a lot of that PM 2.5 health damage is happening at lower levels of risk. So potentially being way up here in this high level is not that much worse than being compressed down to here. But I think we need to ask ourselves if we should expect to see that same kind of effect with socioeconomic indicators. And I think it's important to note that depending on how you calculate this index, different types of people end up being eligible for funding. So if we look at these socioeconomic indicators, their distribution according to whether they were funded by EHD version, which is in purple, or whether they would be funded by a Z-score version, which is in orange, we can see that the places that are currently not being funded based on EHD tend to have lower levels of English proficiency, tend to have less high school diplomas, tend to have significantly more people of color, and tend to have much more population that's living in poverty. So I think it's important for us to reflect that there could be some implicit biases that we're imposing on this data by the choice that we've made to normalize it. And if we look at how these are distributed across space, we can see that the places that would be funded under a Z-score paradigm compared to those that are funded in purple here at EHD tend to be in these more rural areas, which are usually close to agriculture, close to power generation, and often close to or incorporating Native American reservations. So the last thing that I would like to quickly talk about is looking at using an inductive aggregation method of PCA and how that might be different from the current EHD. So just to briefly explain what PCA is doing, it's essentially a dimensionality reduction technique where it's creating linear combinations of our indicators that we'll call principal components, or PCs from here, which is represented in this animation by this magenta line. And this is a version that would have two indicators, just to make it a little bit easier to visualize. And we can see that it's rotating this line in order to maximize the variation, which is the red points, by minimizing the residuals, which is the distance between the points themselves and that PC. And then each subsequent principal component is going to be rotated perpendicularly to the first component, and as such will capture less and less variation as they're rotated. So for this reason, we're just going to focus on looking at the first two principal components of running a PCA on this data set. And the first component here is the y-axis, and we can see that that captures about 30% of the variation in the data. And PC2 is the x-axis, which is capturing about 20%. So taken together, these two components, or these two combinations of our variables, are capturing about 50% of the variation in the total data set. So the way that this is called a biplot, and the way that it can be viewed is, and each of these points is representing the individual indicator itself. And as they get further away from one of the axes, that means that they're having a stronger relationship with that component. And so what jumps out about these two components, it seems that the first component is capturing sort of a gradient in the data of urban environmental degradation. So we can see in yellow here, these environmental exposures variables tend to be pretty far away from the Y, and same thing with the blue and environmental effects, and that there are some socioeconomic factors that are also having a strong relationship with it. If we look at the second component, it seems that it's mostly being driven by socioeconomic deprivation elements of the data. So we can see that these two sensitive populations variables are making a large contribution to it, and that most of the socioeconomic factors, given how far away they are from the x-axis, are likewise contributing substantially. And if we map these, this is for the first component, we can see that it does seem to be capturing kind of this like urban-based environmental degradation gradient, which is like really strongly concentrated throughout South Seattle and in Tacoma. And then likewise in some of these areas of Spokane and Vancouver, and also moving through the Tri-Cities area and in the Yakima Valley. If we look at PC2, we can see that it's more widely distributed throughout the state, with a lot of concentration here in the southeast area of the state, and also some hotspots here that we see in South and South Seattle and Pierce County. And we can notice that really where these areas are lowest are here in North Seattle. Now, if we return to that biplot again, where again, the Y is the first component and the X is the second component, I think it's interesting to overlay our census tracts and see what relationship they have with each of these components. And again, we've used this color scale to denote the classification for funding, where in blue, these tracts were not classified for funding in either versions of the EHD, and in red, they're classified in both. I think it's interesting to note that 98% of these impacted tracks are positive in PC1. So it seems that PC1 is quite predictive of whether or not a track will end up being impacted. And if we look at this upper right quadrant here, which are census tracts that are both positive in PC1 and positive in PC2, we can see that 77% of the impacted tracts fall in there, and that only 7% of the unimpacted tracts fall in there. So I think it's interesting to see that with only 2 linear combinations of this data that are just capturing 50% of the variation, we can pretty accurately classify whether or not a track is going to end up being eligible for funding. So what are the main conclusions of this work? It seems that the current method to use rank-based normalization tends to emphasize the cumulative impact, where things that are a little bit worse than average in many different indicators tend to become eligible for funding, which I think is relatively aligned with the overall philosophy of this index. But I think it's important to note that the type of tracks that would be highlighted in a linear scaling paradigm have different population level qualities. They tend to be more socioeconomically deprived. They tend to be rural. And I think for an indicator that's really focused on environmental justice, the differences that our methodological choice imposes on this data is important to consider in terms of like what it's doing to these populations. And I think it's interesting to see in the PCA that it seems like with the current variables that have been selected for this index, there's really 2 gradients that are being captured. It's this gradient of urban environmental degradation and socioeconomic deprivation. So I think that tells us something about ways that we should be considering new indicators that are added to the index, and what relationship do they have with these current gradients, and are they capturing some different element, or are they just adding to the gradients that we've already included? And also I think it's pretty cool that PCA can classify the impact so accurately, because this is a method that requires much less analyst assumptions, and it also can account for the correlations between these indicators in a way that the baseline PhD can't. So some future directions, I think it's worth considering specific normalization methods that are tailored either by theme groupings or by indicators. And these could be built based on our understanding of the shape of the risk curve, where perhaps a rank-based nonlinear scaling approach is effective for environmental exposures that are superlinear, but maybe it's not effective for these more normally distributed socioeconomic indicators. I think it's worth to discuss modifying the funding threshold, given that we see there's so much sensitivity around that classification. And I think one potential solution for this would be a method that incorporated both the cumulative impact through using rank-based normalization, and also could pick out hotspots by using z-scores that can allow for some of that variation in outliers. And a way to do that would be to tighten the funding threshold, for example, to 10% or to 15%, but then calculate the score both ways and give a census tract their maximum score between the two. So I think this type of method would be able to incorporate both things. And I'm sorry to Joe and Nancy, but it would probably mean that Greenwood is not going to get funding under the HD paradigm. And I think the last thing is to consider using some kind of inductive weighting or aggregation approach that uses some of this correlation structure of the data as a way to upweight or downweight things, or even to aggregate the entire index, because the current index is capturing, as we can see from that biplot, a number of variables that are strongly related to each other. And I think when you use arithmetic means to weight or to aggregate this type of index without upweighting or downweighting or incorporating that correlation, it's possible that you're going to be double counting the same type of effects. So I'd like to stop here and give some acknowledgements. First of all, to my community. This has definitely been a really challenging time and a challenging project for me. And I know that there's no way I couldn't have done it without the support of all these people and their love. And that means everything to me. And I just want to say thank you to you guys so much. I'd like to say thank you to my family. They've always really demonstrated to me the importance of being curious and being a strong critical thinker, even though I think that probably made me pretty annoying to them. So I really appreciate that. And I hope that you guys are proud of this and you can see these qualities in the type of work that I'm doing. I'd like to thank my peer mentors, of which there have been so many, but in particular, Roy, Adrian, Nancy, other people that I've worked with in the PhD program and at IHME. I think it's really going to be hard for me to find another workplace where I can have so many super driven, passionate, curious, and excited people who are just constantly sharing that excitement and that interest and holding me accountable. And I hope that that's something that I can do, but it's definitely something that has meant the world to me in the time that I've spent here. I'd like to thank my committee members. I know you guys are definitely way more busy and stressed than I am. And you guys have always taken a lot of time out of your day in order to help me on this work, even when this work didn't really align with the projects and priorities that you guys are being held to. And so that really means a lot to me. And your mentorship, I think, has taught me a lot and is important. I definitely would like to thank all the different professors that I've had at my 3 tours at UW. I've learned a ton, and again, it's been really meaningful, and a lot of really great supervisors, some of which are no longer at IHME, but I think that you guys taught me a lot about how to be a scientist and like really helped these qualities grow in me. I would like to thank the Department of Environmental and Occupational Health Sciences for giving me a nice, safe landing spot when I left IHME, and for giving me the opportunity to work on this work that I really care about and I think is really interesting. And of course, I'd like to thank IHME for 10, 12 years of really interesting time where it means a lot to me that you guys put me on and set me on this track towards becoming the scientist that I am today. And though things have changed a lot there, it's always going to be a super meaningful place to me. And in particular, I think the PBF program is something that really changed my life a lot and I value highly. And then finally, I would like to thank Hadley Wickham for inventing ggplot, because I could not have done any of this work without him. And I know Bobby doesn't really like it, but I feel like these plots stand for themselves. So shout out to that guy. And now I would like to pause for questions from the public.
Base R is the only kind of R anyone should use. Sorry. So yeah, so right now we have questions again from the public. Congratulations, first of all. That was great. Hopefully people will be clapping at this point, but I'm basically just talking now to fill time while somebody might be asking a question on chat. If you would like to ask a question in person, which is totally allowed, please raise your hand so we can call on you. That's my role here. Again, the questions can be mostly about anything. To fill a little bit more time, I'm going to ask one question, even though I said that the committee is not supposed to ask questions. I was just curious what you thought how important you think it is to have a single indicator that represents environmental health or environmental health disparities, and whether or not some of the problems you addressed couldn't be sorted by having more than one indicator.
I think that's a great question. I think from a statistical and a research perspective, it's not necessarily that important to have a single indicator, but I think one thing that really drives the creation of composite indicators, and in particular the creation of the HD, is things that are really interpretable. And I think that's really where the value of composite indicators comes in, is to decompose things that are spread across like many different 19 different indicators here, and make it one thing that people can point to and generate discussion around. And so I think I would definitely agree that I think like anytime you're compressing all of this variation down into one thing, there's a lot of loss. But I think in terms of making things that are interpretable and can be immediately actionable, and also things that community members can engage with a non-technical basis, is another really important step of this.
Fair. I see a hand raised. Chris?
Congratulations, Joey. That's really some amazing work.
Thanks,
What
Chris.
I'm wondering is, can you hear me okay?
Yep.
Yeah, okay. So yeah, really, really tour de force. What I'm wondering is, if now you take these classifications and you run them backward from those two methods, and you take forgive me, this is a completely naive question, but if you took these classifications and ran them backward, and then used some sort of socially validated measure for where impact has been shown, maybe you do this sort of retrospectively, would it be possible to test like the validation of different kinds of modeling approaches to see where the impact might have been greatest or would be projected to be the greatest? You see what I'm getting at? So
Can you elaborate on what you mean by impact?
Well, I mean, run the machine backward, so you would see so you're talking quite a bit about funding. So the idea with funding is, where you can have the greatest impact in terms of health outcomes on the populations at the census tract level. So you could see where there has been differential funding, and you could see where there have been, larger, smaller changes. And it's just, the question is whether you could now sort of match that up to your modeling data.
Yeah, no, I think that's a really interesting question. So it's difficult to answer within the HD paradigm, given that this funding really hasn't started to be rolled out yet. And so we can't necessarily have information to track that over time. But I think that tracking over time in this paradigm is a super important question. And I think that that also relates to some of the things that we're talking about, for example, like rank-based normalization methods, because I think it's going to be really difficult to, and that's definitely something that the Department of Health wants to do with this indicator. But I think we observe the way that this compresses variation and changes the absolute difference between census tracts. And so I think to use this current method to track things over time is going to be pretty difficult, because while maybe this tract is still higher than other tracts, how much higher it might have been could have changed. And so I think as the Department of Health and other organizations who are using the HD start rolling out these programs, we really need to think about how we're going to use this as a benchmarking and monitoring tool versus this immediate classification paradigm that it is right now. But yeah, the HEAL Act only was created 3 years ago, and so really we don't have data going back that far in order to test it. But I think that trying to run things backwards and see how effective these policies were will be a super interesting future direction for this work.
I mean, thank you for that. I see the complication, but that sort of then begs the question: how will anyone know if they've gotten it right?
Yeah, no, I mean, I think that's a super good question, and it's one that is constantly plaguing researchers that are kind of going back and forth between whether you look for evaluating impact or just monitor the levels of these things. And yeah, I mean, I don't have an immediate answer for you, because I think it's going to be dependent on how we set up these data structures in order to track things as we move forward. And I think another big problem with this index is where the data is coming from. A lot of it is coming, for example, from the census, which is only happening every certain number of years. So it's really not the best tool for tracking things that are changing quickly. Or for example, PM 2.5 is being calculated using these 3-year moving averages, which is definitely an important approach for tracking PM 2.5, because it can be so variable in terms of wildfire smoke and things like that. But at the same time, because you're smoothing this so much over time, it's making it difficult to be seeing immediate impact from these things. And so I think really that's where the community-led element of this work becomes so important, because though it's not necessarily as rigorous and quantitative as the things that we like to do at IHME, I think when you're engaging with these communities that are receiving this funding and seeing what's going on, then that really gives you kind of more qualitative ground truth of how things are changing. And I think we're definitely going to need to be leveraging that in order to respond to things in real time and use these more quantitative metrics as a way to validate those more subjective sources of data.
I see. Yeah. Thanks, Joey. Really fantastic work.
Thank you.
Other questions? To be fair, they do not have to be. They can be about why Joey thinks ggplot's acceptable. It clearly isn't, but
you could ask me what my favorite things are at PCC. I have a lot of choices.
Stunned silence is always good. I'm going to give it another 30 seconds just to sit. PCC is better than Fred Myers.